Today we are learning multi-threading in C++ as we create a bakery. Hi, I'm Ghost, C++ programmer, and today we'll be learning the basics of multi-threading. If you're familiar with the basics, then this tutorial may not be for you, but if you are a beginner or unfamiliar with how multi-threading works, then I suggest you continue. We will be going over not only multi-threading, but a bit of thread synchronization using mutual exclusion, defined as Mutex if you're familiar with the library. I'll explain everything from sequential processing down to parallel processing, and I'll compile and test at each point. You may follow along and code with me, or I'll leave a link to the repository in the description below. With that said, let me show you how it works. Okay, so the first thing I'm going to demonstrate is sequential processing, which means we're going to run everything on one thread. And now I have 4 bakers who are going to bake up to 20 pies. So you're going to see how they process and how long it's going to take. Okay, so we'll run the program and immediately you can see that baker 1 was baking, baker 2, then baker 3, and baker 4. Now in the results, you see that we did bake all 20 pies and the total time took 7.7 seconds. But if you notice the processing, you can see that baker 2 had to wait for baker 1, baker 3 had to wait for baker 2, and baker 4 had to wait for baker 3. So they had to wait for each other because you could think of it as the kitchen is very small and only allowed 1 baker at a time. Thus they had to wait for each baker to finish so the next baker could come in and make their 5 pies. Which, by the way, each baker could only make 5 pies, and that's what you see here. You see baker 1 completed all their 5 pies before baker 2 was allowed to enter the kitchen and complete their 5 pies, and baker 3 and baker 4. Okay, so let's see how parallel processing does. So we will run the program again. This time you see it happening much faster. And if you look at the results, you see that we still baked all 20 pies, but this time the total time was 2.1 seconds versus the other one that was like 7.7 seconds. And if you look at the processing, you can see that baker 1 was baking pie 1, but baker 2 was able to jump into the kitchen because there's enough room now. So baker 2 was making pie 2, baker 3, baker 4, and you can see as you keep going, they keep flip-flopping because they all have access to the kitchen and they're working in parallel. So how multi-threading works is that it uses your CPU cores and it splits that one task across multiple cores, which then work in parallel of each other, get the answer, and return back to the main thread. Now that's a very high level view of how it works. Of course, there's other things like hyper-threading and it goes deeper than that. But essentially, you can think of it as if you have your main program without multi-threading, it's only running on one core and it must complete every instruction on that one core. But if you have a huge task to complete, you can use multiple cores of your CPU, spread that task across those cores, get the answer, and return back to that main thread. Now in C++, it is very simple. There is a library called thread. All you need to do is include that, and that'll give you access to create multiple threads and also do things on the current thread that you are on. Anyways, let's jump right into it. Okay, so here we are in VS Code. I have some boilerplate that I can go over. First things first is that I am using G++ to compile. Now, if you use something else to compile your code, that's fine. You're more than welcome to use that, but this is what I'm using. Now, if you already have that set up, I have simple bat and shell files here that allow you to compile and then run the program. So basically with this bat file here, all it does is make sure that this directory exists, which will be the output directory for your executable. And then it uses that G++. You run bat files very simple. It just checks to make sure that the executable exists. And if it doesn't, it exits early. And if it does, it just starts it. Now I do have these in shell scripts, as you can see here and here, just in case if you're on Linux or Mac. Anyways, back in our main.cpp file, I have these libraries up here, which you don't need to worry about the random or this IO manip. You don't have to worry about this function here. It's not part of the tutorial. It's just something that I use in order to get a random time in milliseconds. You'll see why later on, but I'm not going to explain how it works because it's not a part of this tutorial, but you must copy it. So if you are coding with me, I'll give you a second to copy this. Okay, besides that, we do have our thread library, which will allow us to create threads. So you must include this as well. And then lastly, we have our main function, which is the entry point. Right now it's empty. We will build it out once we build this other function first. Okay, so the first thing I'm going to start with is sequential processing. I'm just going to build the bake function first, which is going to represent each individual baker, and then we'll move into parallel processing and thread synchronization and other things as we go. I will also compile and test at each point. So the first thing we're going to add is some global variables that will be shared across all the threads. We're going to start with a variable of type integer called pies per baker, we will set that at 5 because if you remember, as I explained earlier, each baker is only going to be allowed to bake 5 pies at a time. So this is what this variable represents. Next variable is type int. It's going to be called pies baked. We'll set that to 0. Now that's going to track how many pies we baked in total across all bakers. The last variable we're going to create is another type int. It's going to be called number of bakers. And we're going to set that to 4 because there's going to be 4 bakers. Now this variable doesn't do much. All we use it for is to multiply by the pies per baker. So that way we know how much pies we need baked. In this case, it's going to be 20 because 5 times 4. Okay, moving on, the next thing that we need is our function. So we're going to call that function return type void. We're going to call that function baker. We are going to have a parameter. It's going to be type int ID. And that's going to represent the baker's ID, so that way we know which baker is doing what. Okay, next we're going to create a for loop, so that way we can iterate how many pies this baker is making. So we'll say for type integer I equals 0, and then we're going to say if I is less than pies per baker variable, which remember is 5, and then all we're going to do is increment. Next, what we want to do is get some random time, which we're going to utilize this function up here. So we're going to create a variable. We are going to call it work time equals that get random work time. I will explain why we need that very soon. Next thing we're going to do is print to the console, so that way we know what this baker is doing. So we're going to use cout, std cout, and then we're going to start with ... baker, insert the ID at this point. Then we're going to insert another literal and say is making pie number, insert the pies baked plus 1 because we didn't bake it yet, and then I'm just going to insert the line break. Okay, next what we want to do is we want to simply increment that pies baked, which remember is the total amount of pies that we baked across all bakers. Last thing we want to do is that we want to simulate something is happening here, because if we don't, it's just going to exit this function too quickly. So we want to cause some delay. So we're going to use a function called sleep4, which is part of the thread library. So let me write it out and I'll explain it. std this thread, which refers to this thread that we currently are on. We're going to use a function called sleep4, which is going to allow it to halt at this certain point in the code. Now we're going to use this library called chrono, which I'm not going to go too deep in, but it's pretty much about timing. So it's going to be std chrono, and we're going to access the milliseconds. We can access seconds, hours, minutes, but we want milliseconds just because we want it to be much quicker. Now what we're doing at this point is creating an object of milliseconds of chrono library in order to pass into the sleep4, because that is what it accepts. Now relating back to that work time variable that we created up here using that get random work time, we're simply going to take that and pass that in as an argument to this milliseconds object and close it out. We are done. To understand really quickly what work time is going to look like, you can look at this function, and specifically like this area right here, it's going to be any random number between 250 milliseconds to 500 milliseconds. 500 milliseconds represents as half a second. So you're pretty much going from a quarter to a half a second. Now I simply could have had some fixed time and just put 500 milliseconds, but I don't want every baker to have the exact same time. I want it to be some variable going on there, so that way the simulation feels a little more real, and some bakers may be a little bit slower. And that's why I have the variable inside the loop, so that every pie that they're baking is different. The point I'm trying to make is that it's not that important, but it just made the simulation a little bit more realistic. Okay, so let's change that back to work time, so that way it is varied. And we are done with the baker function. Let's move on to the main function. So the first thing I want to display is that little message that says bakery is preparing order. So we're going to use cout and say bakery is preparing order ... add the line break. Okay, the next thing I want to do is simply for tracking how long the program takes. So I'm going to write this line of code and I'll explain what it does. Okay, so all that does is it uses the chrono library again, which remember is timing. It uses this high resolution clock, which is a high precision clock. And then it uses a function now to get the current time right now. We're going to use this and set it to start, because later on after we run everything, we're going to call this again and set it to end, and then find the difference, and that will be the time. Okay, so next all we're going to do is call baker 4 times because we're trying to represent 4 different bakers. So we'll say baker, pass in 1 because this is baker 1, and we're just going to copy and paste for the other ones to make it quicker. Okay, so we have baker 1, 2, 3, and 4. Next, we're gonna call this again and set it to end because we're done processing. So I'm just gonna copy and paste this here, call this end. Now, the next thing we wanna do is find that difference. So I'm just gonna write this out really quick. Okay, all that really does is use the chrono library again, uses an object called duration, and we gotta pass it of some type. In this case, we're gonna use double. We're gonna name it elapsed and then find the difference between the end and the start. Okay, the last thing we wanna do is print all the results out. I'm actually gonna copy and paste this because there's no point in writing it out, and then I'll explain how it works. Okay, so what we have here in this first printout is that we are printing out the results, and we're just using these line breaks here, so that way it just looks neater. Begin with this first line break to separate it from all the prints that we're gonna see from these functions here. And then we line break it again, and then just create some space so that way it's nice and neat. We have the total pies baked, a little divider, so that way it looks nice and neat. And then right here, this is the part that I was talking about earlier up here with our variables, where the number of bakers, multiply that by the number of pies each baker could make, and that will give us 20 in this case because it's going to be 4 bakers and they could only bake 5 pies at a time. The last thing we have over here is just the end line. Now for this one, we want to print out the total time that it has taken for the entire program, in this case between the start and end right here. So the first thing we're going to use is this set precision. Now real quickly, that just came from this library here, the IO manip, because we are manipulating the input output, and there is a function called set precision which allows you to set the amount of precision, because in this case the elapsed variable here is going to give us some long number, so it can look like, let's say it's 2 seconds and something, it'll look something like that, and we don't want all that. We just want to look like this. We pass in a precision of 2 and it'll look something like that. And all we do here is just have this literal total time, and in the elapse you have to use a function called count. I'm not trying to go too deep into that, but you just have to do that to get the actual count out, and then we just insert an S for seconds, and that's it. Okay, let's test this out. Okay, so since I have those bat files right here, the compile and run, I'm just going to use that because it's going to be much quicker. So we will say .compile. Okay, so it finished. Now if you look, you see we have an out directory with the bakery.executable right there. So now we can simply run the .run bat file or shell file, whatever platform you're on. So as you see, baker 1 is baking, baker 2, baker 3. Okay, so the reason why it shut down that quickly is because we forgot to put something. Now, right before we return and end the program, we're gonna add this system pause. All it's gonna do is pause the terminal from closing and expect the user to input enter. That's only so it doesn't close down like it just did. Okay, so we compile again, and then we're gonna run it again. Okay, so baker 1, baker 2, baker 3, once again, all sequential order, and there we go. Okay, so we finished all 20 pies, but it took 8.3 seconds. So we can reduce the time and make it much quicker. Instead of waiting for each baker to have to wait for the last one to leave the kitchen in order for them to come in and start baking their 5 pies. And that is what we're gonna do next. Okay, so back in our main.cpp file, we want to utilize multi-threading, which is from this thread library here. So what we're gonna do is get rid of all of this because we don't wanna call it sequentially anymore. We're going to delegate these tasks to these other threads and allow it to run in parallel. So in order to do that, we're gonna create a thread object. It's gonna look like this thread. Now each thread represents 1 baker, so we're going to call this baker 1, and all we are going to do is pass in the function that we want it to run, and in this case it's going to be called baker. And as a second argument, since this baker function does have a parameter, which in this case is going to be baker number 1, that's all you need to do. Now what that does is not only create a thread, but it also runs it. So what we're going to do is copy this 3 more times, so that way we have a total of 4 bakers. Okay, so now we have all of our bakers, or I should say we have all of our threads, and they are all running, but there will be an issue here, and I'm going to show you first by compiling and testing and then explain what the issue is. So we will compile and then we're going to run. All right, so as you see, this is the issue. It looks kind of crazy. You can see this press any key to continue, which should be at the very end. Remember, that comes all the way at the end, but you're seeing that right here, and then you're seeing this result on top of it, and then, you know, you're seeing bakers that we're trying to bake. So what's going on? What has happened is that our main thread, which is this right here, the main function here, it's continuing without waiting for these other threads, which we have here, 1, 2, 3, and 4, to return back. So basically we are creating these threads and continuing running this line, and all the way to the end here to that system pause. Now, as you see, we don't want to do that because it becomes very chaotic. We want the main thread to wait for all the other threads to do what they're supposed to do, then it gets all that information back and then continues from here. Now, in order to do that, it's very simple. All we need to do is call this function called join per each thread. Now, what that's going to do is wait until that thread is complete, meaning that it reached the end of this scope. Once that happens, then it can continue to check the other thread and make sure that one is complete, and then number 3 and number 4. And once they are all complete, then we can continue this main thread here. So how that looks is that we're going to use these variables starting with baker1, and we're going to call that join function here. Like I said, what it's doing at this point is waiting for this thread to be completed, and it will stay at this line until it is completed. But if I just do that and say baker1 join, and I don't do that for the other threads, then it will wait for this thread. But if the other ones are still running, we're going to run into that same issue where it's just going to continue the main thread and ignore those other threads that could possibly still be running, and then reach the end of the program. So we're going to copy and paste this one 3 times. We will change the names of them. So this one is number 4, this one's number 3, and this one's number 2. So now the main thread is going to wait for every thread that we created to ensure that they are done executing before continuing the main thread here. Now, if we compile again and run it, we should see it working correctly. Now, it looks crazy because there is something else going on here, but we did solve that first issue where all the threads did run, starting with that first print here, the bakery is preparing order, and in each thread technically they did run before we reach the end, the results, and then we see that we did do 20 out of 20, and the total time is 2.1 seconds, which by the way is much faster than the, what was it, like 7.7 seconds or something like that. And then finally the press any key to continue. So it does work, but what's going on here? Why it's not looking nice? We see baker and then ... baker 4, and then is making pie 1, and it looks crazy, right? Well, that's what we call a race condition, which segues us into thread synchronization. Okay, so what is race condition and thread synchronization? What is going on there? So basically what is happening is that each thread has access to the same variable, because remember, we have global variables, specifically the pies baked variable. So what's happening is that each thread is accessing that same variable, but remember, it is working in parallel. So imagine if this thread here and this thread here, which is at the very same point in execution, is accessing the same shared variable here. What is happening is that this one is trying to update it while this one's trying to do the same thing. This causes a race condition. They are racing to that variable, trying to operate and trying to do something with it. Now, this could lead to drop updates, meaning that it won't accurately reflect what it's supposed to be. And in this case, we know that it's supposed to be 20. So in some cases, it may drop to like 19, 17 or something like that. Now, it doesn't happen all the time. And in this case, it was still 20, but that's because we're using a very low number. But if we were to try to do something much larger, it would probably happen more frequently. But what about the printing? Why was it all over the place? Well, if you think about it, that operation is also shared as well, because there is only one C out. So if both threads, once again, in the same place are trying to access that C out and trying to print to the console, they're going to overlap each other, and that is exactly what you saw. So what we need is thread synchronization, which essentially tells other threads, hey, don't operate on what I'm trying to operate on, any global variables or global operations, because I'm using it right now. Once I'm done, then you can use it. Now, we can accomplish this using mutual exclusion, and in C++, the library is mutex. So you're probably wondering, what is mutual exclusion? Basically, all it is that it's a locking mechanism that ensures that only one thread at a time can access any shared resources. In this case, that variable that I was referring to, the pies baked or the C out. And what it does is it protects that variable or that operation from any other thread accessing it and doing something to it. But it does have some drawbacks. It is expensive, meaning that it will make your overall execution slower. And if not used correctly, it can create thread blocking or worse, deadlocks. But that's something for another video to go over, because it does get a little more crazier. And this program, we're gonna keep it very simple, but I will go over those basics and prevent any blocking, deadlocking, and how we're using it is not going to create that much overhead. Anyways, let's implement it. Okay, so back in our main.cpp file, the first thing that we're going to want to include is that mutex. Next thing we want to do is create a global variable for the mutex, so that way each thread has access to this locking mechanism. So we'll do that right below these global variables. say std mutex, and we'll call it mtx. Okay, so next we're going to open up our Baker function. Now we need to look at what point of this function is causing the issue. And to remind you, we are referring to anything that's global. So in this case, we're using cout, which that is a global operation. So that matters. So let's just create a space there. And the next thing that matters is this pies baked, because remember, this is global as well. Other threads have access to this variable and this operation. So we're going to isolate these things here. Now the way I'm going to use mutex is that I'm going to manually lock and unlock it. There is another way, but I'll explain that later on. So all we need to do is say mtx.lock, and then right below it, because this is all that matters is this portion, is that we're going to use the mtx again and say unlock, and that's it. Very simple. So at this point, what happens is, let's say this is thread number 1. Once it reaches this, and this is the first thread that makes it, we will use this global mutex, which we have up here, to lock out any other threads from accessing this portion. So if any other thread reaches it, it won't be able to access it and it'll stop. And this current thread that had locked it will continue to execute. And then once it's done, it will unlock it, allowing any other thread to have access, which will prevent that race condition. Because remember, if other threads are accessing this cout at the same exact time, then that's when you get that weird printing happening, what you saw earlier. And we don't want to include this into the locking mechanism, because if you think about it, if we do include this inside the locking mechanism, what is going to happen is that the thread that ends up locking it will perform these operations here, but at this point it will sleep for whatever time it has to sleep for, not allowing any other thread to do its job. So essentially what we're doing is reverting back to sequential operating rather than parallel, which completely negates the whole entire point of this. And what that's called is called thread blocking. So that is why you have to be very careful with how you set up your thread synchronizations. So in this case, we're going to return that back down below, so that way we don't cause that thread to block. Okay, so we are done. Let's compile and test. Okay, compile and run it. Now, as you see here, we got the parallel processing because each baker intertwined, they are all in the kitchen working, and we don't have that weird printing because they are not racing against each other. That is because we are locking it each time and then unlocking it to allow other threads to continue, and it works perfectly. We are still baking 20 pies and the time is still good. It's not 7.7 seconds, it is still 2.1, meaning that it is working parallel and we're not causing any race conditions. We have true thread synchronization. But if you recall, I am locking and unlocking manually, and that is not good. In 99 cases, we don't do that unless you really had to add some custom logic. But there is an alternative, and it's called lock guard. And what that does is it locks and unlocks automatically for you, but as a bonus, it handles any exceptions safely. And that is what we're going to implement next. Okay, so we're going to go back into our Baker function. So as you recall, I am locking and unlocking manually by using these functions, the lock and unlock, and wrapping it in between the portions that matter. So we're going to remove these. So we are going to use this thing called the lock guard, as you see here, which is an object. And now you need to pass in the type. In this case is going to be the mutex, because that is what we are passing in, and we're just going to call it lock. Now what you need to pass in is that global mutex variable, so we will pass in the mtx, and that is it. So what is happening at this point is that it is constructing this lock guard. So when you pass in this mtx in the constructor, it will call that mtx.lock function for us, but it'll also do these other things where it'll handle any exceptions should they arise. And now to unlock, it is handled in the destructor. So this is where you have to be very careful, because if you think about it, in order for the destructor to run, we have to go out of scope. Now that's assuming that you know how stack variables work. So this is a stack variable and it will exist so long as this scope exists. So once we reach the end right here, this variable up here and any other variables like work time will disappear. So this is where the unlocking will happen, because what's going to happen is this lock guard object, the destructor of it, will be called once we reach this point, and then it will unlock. Now, if you can spot an issue that will happen, I'm gonna give you a moment, put it in the comments. Okay, the moment's gone. So the issue that will happen is that this right here will be a part of that lock. So remember, going back to the other case, if I did it manually and I locked it at this point, let's say I locked it here, and then at this point down here we unlock it, what is happening is that this will be a part of that lock. So essentially it will create a thread block, meaning that this thread will block any other threads from accessing until it is done waiting, which for extra clarity will negate the whole parallel processing and go back to sequential processing, which we don't want, right? So now how do you do this? How do you deal with that? Like if we want this here and we have to create this lock here so that way this is protected, how do we deal with it? How do we not include this a part of the lock if there's no way to unlock because it happens automatically? Well, it's very, very simple. All you need to do is create a nested scope. And if you remember from one of my last videos, I'll leave a card above, I believe I did discuss how nested scopes work somewhere in that long video. But as a refresher, you could include scopes anywhere. There is a scope. So at this point, if you create any variables inside of it, and then once you exit the scope here, those variables will disappear. So I can create a scope and another scope and another scope and another scope. Now I just keep going. I can create scopes and scopes. Literally can create scopes anywhere as long as you use the brackets just like that. Anyways, so if you see where I'm going with this, it's very easy. All I have to do is copy and paste this stuff up here into this scope right here. Now essentially what we have is once we enter this scope, we do in fact lock, but it only affects these two things here. And then once we reach here, this is the point where it will unlock because we do call that destructor, which is of this lock guard object, right? And it's not unlocking here, so we can delete that. So then once we come back out of the scope, the lock is completely removed, allowing other threads to use this MTX and then lock it once they're at that point. And then this thread can simply wait without blocking any other threads from continuing. Thus, we now have parallel processing. Okay, so to make sure that that works, we are going to compile and test, and we should have the same results as the last one. So we will compile and we will run. Okay, and we see that it works perfectly. So each baker is in the kitchen, they are baking their pies, they are working parallel to each other, and then at the end we do end up having our 20 pies, which is what we expect because we have 4 bakers that can make 5 pies at a time, and our total time is roughly the same as last time, which is the parallel time that we expect, the 2.2 instead of something like 7 point something or 8 point something. So it works. If you made it this far, then this is a understanding of how multi-threading works, as well as threading synchronization. Okay, now for fun, what I want to do is I want to introduce more bakers to the kitchen and reduce the time even further. And I want to do it so that way we are still creating those, or say we are still baking those 20 pies, but now we have double the amount of bakers in the kitchen. So the first thing I want to do is create a new global variable. It'll be of type int called pies needed, and we'll set it to 20. That is going to be used in our for loop, so that way we know once we reach 20 we will exit and no more bakers can continue to work because we reach our goal. So we're going to open up the baker. So remember, this is another global variable, so we need to protect it, meaning that we are going to put it right under our locking mechanism. So all we're going to do is check if the pies baked, which is our total, is equal to the pies needed, which is the amount that we need, which is 20, then all we're going to do is break at this point. And we want to place it here because we don't want to do the work. We don't want to see this, and we don't want to increment. We want to check here so that every thread that reaches this will do this before leaving. Matter of fact, we can change the break for return, which will just return completely outside this function instead of breaking and then sleeping. So that way we drop what we're doing. We are done. All bakers leave the kitchen because we completed our objective. We baked 20 pies. Okay, so the last thing that we need to do is create these additional bakers. So let's go into our main function here, and we're just going to copy and paste this and then change everything. So this will be 5. Now remember, we have 4 additional bakers, meaning that we have 4 additional threads, and we need to double check to make sure that they are done, because if we don't, what is going to happen is that this main thread will continue. So do not forget that we have to add 4 of these joins here. So I'm just going to copy and paste this here, and then we're just going to copy and paste these. So I should probably get better with shortcuts because I know there's a much easier way of doing this. Okay, so we're done. We have our 8 bakers that we created and begin working in the kitchen. Remember, now we have a bigger kitchen. So they begin working and baking their pies. This main thread at this very point here is not going to continue. So you can think of it as it's not going to reach out to the customer and give them the pies, because we need to make sure that they're done, that they're baked. So we're going to check, starting with baker 1, are you done baking? Okay, you're done. Let's move on to baker 2. Are you done? Now at this point, baker 2 could have been done a long time ago, but we just need to check here anyways. So we're going to continue to check and make sure that every single thread or baker has completed baking before we continue to move on with this main thread, which essentially you can think of it as giving the pies to the customer. Anyways, let's compile this and test it. Okay, so we compile and now we're going to run it. But remember, what we should see is a much faster time, because we have 8 bakers in the kitchen making the same amount of pies, the 20 pies. So that's double the workers with the same amount of output, meaning that it should be much faster. All right, so let's run it, and boom, it happened so quickly I couldn't move that window. But yeah, look at that, 1.3 seconds. Now what were we getting before? I believe it's like 2.2 or something like that. So it is much faster, and you can see them here: baker 1, baker 6, baker 7, 8. They're all working in parallel, just trying to create all these pies, get the order done, because the customer is hungry, right? So we completed it much faster. The customer is happy, and the customer is going to come back because we're working in parallel processing, or I should say we are working in multi-thread. Well, that's it. We're done. This is a much shorter video in comparison to my last video, which I'll leave a card up there, where I created a maze generator. I believe that video is like an hour and like 20 or 30 minutes, but I wanted to create something that's much shorter and covers one concept at a time rather than a bunch of concepts being thrown out at you. But I'm very new to all this with YouTube, with recording in front of a camera, with trying to articulate all these technical concepts. So I'm going to try a bunch of different things, and I hope that this one is more clear. And if it is, then maybe I might make more shorter videos like this rather than longer ones, and in the future make longer ones. I know it depends on the project. Of course, if the project is a very big project, then it must be a longer video, but I'm thinking about making the projects very short and center around like one concept at a time. But I don't know, you let me know what you think. Anyways, this video is about multi-threading basics, meaning it's very beginner level. It goes deeper into like other things like atomic, recursive guarding, and just a bunch of other concepts that I can maybe make a little bit later on. But I just wanted to give a little brief introduction to the library Mutex and the library thread in C++, as well as a little bit of background of how multi-threading works. So I hope you found it helpful. If you have any questions, please let me know in the comments. The repository should be in the description below, so that way you can just download it if you didn't want to code with me, or if you just need access to those bat and shell files, then you're more than welcome to go on there and download those. I also want to mention that I do have a Discord server where I have over 100 members, and that's a place where like-minded people like us can come together, communicate ideas, and share knowledge with each other. You can directly contact me on there and ask me anything you want to ask me. I'll leave a link in the description below so you can join it. And if you haven't checked out my last video, that is where I made this maze generator. It is pretty lengthy, so if you don't want to do that, I trust me, I understand. But there is another video that I created about like 2 weeks ago, and that's like a password manager, simple one for like beginners. I believe that one's like 20 minutes long, so if you want to do that one, I'll leave that up there as well, like right now. Anyways, if you made it this far, thank you for watching. Thank you for supporting. If you subscribed, if you haven't, please consider subscribing, because I am going to be doing this for the long haul, and it'll be great if you come along for the ride. Anyways, I'm Ghost. I will see you in the next video.